right. Greetings, everyone. Thanks for the beginning of the afternoon session of VulnCon 2024. I have the distinct pleasure of introducing Andreas, Joyabrata, and Vineeth. And the topic in this track today is going to be finding, managing, and preventing vulnerabilities and automotive perspective. Our presenters are remote, so if anybody has any challenges or issues with audio or visual, please do shout out. We have AV here in the room, and we will handle anything that that we need to handle. So a couple of announcements before we start. Please be aware that session surveys are available in the conference mobile app via QR codes found on table tents in this room and elsewhere. These are really important to us, especially as this is our inaugural VulnCon. We are really relying on honest feedback from our participants. So please tell us what you are thinking, and then we will continue to adjust as we go forward. Cell phones, obviously, is a courtesy, right? Make sure your cell phone or laptop or other devices aren't making sounds. Please note that all sessions, this one also is obviously live streamed, right? And we also have remote participants outside this room. So if you ask a question, you don't have a mic, no one's going to hear it. So we'll be around with microphones during Q&A session. Most of the time, well, we don't really take questions during the talk, but if there's Q&A, I'll be around with a microphone. But just know, if you don't have a mic, no one can hear you, especially our remote speakers today. All right, with that, we will kick off to our presenters.
Okay, thanks for the introduction. So we will talk about automotive vulnerabilities. So next slide, okay. So who are we? A short introduction. I'm Andreas. I work in CARIAD since 2020. Before that, I worked at Audi, and before I did academic research, Ph.D. in the university. And my current occupation is I work in vulnerability management. I help with fuzzing, CI/CD testing, and I also was a developer. I developed an IDS system for our current car generation. Joy, sorry.
All right, yeah. So myself, Joyabrata Ghosh. I recently joined CARIAD, and before that I had around 6 years on automotive electrobit on the Linux operating system developed for multiple OEMs. Before there I also worked on SBOM security and legal aspect. Before that I worked on embedded and open source security aspects over 10 years, and then give the hand to Vineeth here, my colleague.
Yeah. Hello everyone. I'm Vineeth, or Vinny in short. Yeah, even I was part of the, or have been part of the VW group like since 2018. Started at Audi in the same team as Andreas, and then transitioned into CARIAD, and yeah, currently like have been part of the offensive security team, doing some investigations on our cars, and also yeah, part of the vulnerability management team, trying to manage and find vulnerabilities. Yeah, and also like as another role, like I'm also partly looking into the China GPT regulations that are affecting our cars, and maybe we'll also speak a little on this later. So yeah, thank you. Now back to Andreas.
Yeah, so now you know who we are, and now just a short introduction to our company. So we are at CARIAD, and CARIAD, like, we provide the software and also part of the hardware of the Volkswagen Group. Currently, there are like 9 different brands, from Porsche, Audi to Bentley, Lamborghini, Volkswagen, Seat, Skoda, Cupra, and I think also recently, like, there's a new brand in US called Scout. And yeah, so we have like a lot of cars on the streets getting the data for the advanced driver assistance system, and the goal is that we have like one software platform which is used in all the cars of the Volkswagen Group, so that we can use the scale effects of this huge group. And we are currently 6,000 employees. We have a lot of nationalities. We are mainly based in Europe, but also we have departments in US, India, and China. So now you know our company. So this is the agenda for today. I will first introduce some automotive specialities. So what is the architecture we are using? Then we will dive into some problems or weaknesses, vulnerabilities we have in the automotive space. Then Joy will tell us something about the automotive supply chain, the whole SBOM VDR VEX thing. Then Vineeth will tell us something about the vulnerability management we do there and the lessons learned, what we experienced the past years. So a short disclaimer, the content and the vulnerabilities we present in this talk are all publicly known, so no secrets in here. And maybe if you have some opinions, they may be our own and not of our employer. So just keep this in mind. So what is the automotive architecture? We started with the CAN bus. It was invented some years ago in 1986 by Bosch. It's a very simple field bus, 2 twisted wires. It's cheap and simple, and it's priority based. So on the right, you see the actual code struct in the Linux kernel. So we have an CAN ID, which is over 32 bits. Out of this 32 bits, 11 bits are for the address, and it's priority based. So the ID 0 has the highest priority. If all 11 bits are to 1, this is the lowest priority. Then we have a length field from 0 to 8 bytes, then some padding, and the end there's 8 bytes of data. And yeah, so everyone who is on the bus can receive the messages and can read it, and there is no security implemented by design, and there's only some CRC check for detecting bit flips on the bus, but no security. Yeah, so the classic automotive architecture was there was one central gateway, then you have like buses like CAN bus or LIN bus, then you have your ECU. So ECU is like the electrical control unit. And so overall, it's a very distributed systems. In some systems, you have like 100 different ECUs, which are connected over different buses, and they communicate with each other. This is the classic one. So where also you buy several ECUs from different vendors, and in the end, the OEM plugs them together in the car and put it to the street. Then a more modern approach is that you already have like domain controllers, which are a bit more powerful. For example, the infotainment system, advanced driver assistance system is like one domain controller. And then under this domain controller, you have another different ECUs, and the domain controller itself are connected over a service-oriented gateway. There already you have like something like automotive Ethernet, some IP. So in the service-oriented way, you don't always send the signals if they don't change. So only you can subscribe to a service, and once there is a new event available, all the subscriber gets the event sent to them. This is what we mainly have now on our streets, and in the future, or like some architectures already like this. It's more a zone architecture where you have one central component where all the different domains are not mapped to one dedicated controller, but it's more spatially distributed. So you have in the corners of your cars, I have so-called zone controllers, which deal with the sensor actors in the area of this car, and then the central compute is done in one big computing platform somewhere in the car, and this reduces the wiring harness, and also it enables that you can easily update functionality and have like, yeah, the updatability is easier, and you can add more functions easily. So this is the future, what like every car manufacturer is going to, and also it's known as the software-defined vehicle, which is like a hot topic at the moment in the automotive space. But it doesn't stop in the architecture in the car itself. You have a lot of environmental stuff there. You have like a own diagnosis system. You have smart keys. You interact with other vehicles. You interact with infrastructure. Of course, there are end-to-end services. You have something in your backend systems and so on. But we will focus mainly in this talk on the car stuff itself. This is also what we do in our day jobs. We focus on the product security of our car, the backend stuff, and our office clients and so on. It's not our department. Oh, my next slide is not working. Okay. So the operating systems, what we use normally in the past, it was more like dedicated operating systems for cars. So stuff like AutoSAR, which are adapted and classic, different flavors. This is more a runtime environment and yeah, middleware. Also, there's like real-time proprietary systems like QNX or VxWorks, but also at the moment there's coming more and more Linux-based systems. In the infotainment, we have like Android Automotive, so there's more common operating systems, what you have also in other worlds like mobile. And also the trend is that it's not only closed source you buy from a supplier, but also there are several open source initiatives which different vendors and also tech players like AWS, Microsoft, ARM, Red Hat, you can collaborate on different open source projects and also work on non-differentiating software components so that not everyone has to invent the wheel there again and again and have the same vulnerabilities every time there's a new car generation. So let's dive into the vulnerabilities. I think last year there was a pawn to own. They also have an automotive track. And in one track, like some competitors, they run Doom on the infotainment system. So your infotainment system definitely can run Doom. And they found 2 bugs and could exploit it to run Doom there on the infotainment system. Also going back, the first thing, car hacking stuff with like a paper from 2010, where some researchers showed that the CAN bus is vulnerable to a lot of attacks and that they can display on the instrument cluster arbitrary speeds and also can control the mileage stuff there. Then one of the most famous car hacks, like that was done in 2015. So there was a Black Hack talk, and also I think in Wired magazine, some researchers, Miller and Velasek, they showed that they could remotely steer Jeep. So this is every car hack talk has this specific hack in it. So here it is. And yeah, so coming more to the current thing, so the CAN bus thing is still a thing. So this was from last year, where there were some thieves. They unplugged some headlights connected to the CAN bus, and then they could unlock the car and steal the car in UK mainly. And there are devices you can buy on the internet which make it very easy for the thieves. So they just need to find the 2 wires, connect to them, press a button, and then you can steal the car. And this is blamed to the insecurity of the CAN bus. Coming also to some vulnerabilities from our group, there was like in the iCar 3 and VW car, there was some problem with the REST API which was not authenticated, and then you can send like requests there, and then the user could not change the volume anymore. Another example, that's also classic car stuff, is that there's some hard-coded credentials in the firmware. So the UDS port here, that's an diagnostic port, then was not, yeah, if you can read the hard-coded credentials, you can connect to the UDS port and can do then their unauthenticated access. And of course, we also use curl. Last year was also this announcement that, yeah, there's a high security vulnerability in the curl project. Later, then the maintainer had a very nice blog post where he detailed what the root cause was, and the thing was a buffer overflow, I think. And he stated that like 41% of the security vulnerabilities in curl are related to memory safety issues. So if they would have written it in Rust, we wouldn't have this 41% of the issues. But of course, on the other side, you cannot rewrite curl on a weekend in Rust. So this is also not going to work. Another prominent vulnerability was an issue in the glibc. Again, another buffer overflow with environment variables. Yeah, it was also last year, and the researchers who found it said that they could rediscover this vulnerability with a state-of-the-art fuzzer like within seconds. So that leads us to the next question. So what is the root cause of some automotive vulnerabilities? Here is the top 25 most dangerous software weaknesses. I picked some of which I think from experience are relevant for us. So you see that I didn't use like cross-site scripting and stuff like this, because there we don't have such a huge attack surface. But again, we have a lot of memory safety issues. There's OS command injection, which was part of the GPAC, for example, and proper input validation, and hard-coded credential is also there. And this is from the general list and from a specific paper from 2019. And their methodology, they had this different categories. And for each category, they had certain search terms. And then you can search the vulnerability database for these specific search terms and then see what CVEs you can find. The original study was done in 2019. I did it last year with more data from the 4 years in between. And so this is what the outcome was. We see that after filtering out a lot of false positives, there are a lot of Bluetooth issues. So 66% of the found vulnerabilities I found with this methodology were due to Bluetooth. There were a lot of problems with the chipset firmware, for example, in the Snapdragon and the Exynos. So it is from two vendors who build firmware for chips. And we see that from the OEMs. So this is all the brands who produce cars. They only make 3%. So I think a lot of them are not really reporting CVEs and are not assigning CVEs. So maybe they are not so open to report as other vendors who produce Bluetooth and chipsets. To drill down a bit here, when I did all the filtering and try to detect false positives, I had like this in front of me. So you don't need to read it, but basically it's always the same. It's the CWE 125, and it's an out of bounds read. And this is a bounds checking in Bluetooth, and it seems to be really hard to get this correct if you have this untrusted input, and you need to do the bounds checking probably in C, and then a lot of mistakes can happen there. If we print this over time, then we see that before 2014, there were like almost no vulnerabilities for these keywords, but after Open Heartbleed from OpenSSL, a lot of researchers started to do fuzzing and do a lot of research. And then we see the reddish part here. It's mainly to memory safety issues, and only the blue and gray part are about improper authentication and missing authentication and so on. So we see the memory safety issues are dominant over the years. And here it's another graph where we sorted it by overall number of CVEs according to the CWE classes, and the most dominant was the 119, the buffer overflow, followed by out of bounds reads. And then the non-memory safety issues are the improper input validation and the exposure of sensitive information. And then again, we have some use of the free and other memory safety issues. So if we could handle memory safety issues and improper input validation, like we would have a lot of the cake already cut down and could focus on the other parts of the vulnerabilities, of the weaknesses. So I mentioned memory safety a lot, so a bit detailed memory safety. What is memory safety? So memory safety means that all your memory access are defined. So in practical means are that you have runtime bounds checks, you check before you dereference your pointers, and you also have lifetime checks. In C, if you have like unchecked pointer arithmetic, you don't have any of these. And if you detail it a bit more, you have like two parts. You have spatial memory safety. This is all to bounds access. So you need to access the object within bounds. There is a lot of also work in C and C++ how to add this dynamic bounce checking, and you can have some hardening mechanisms in your compiler that you can check for this. And the second part is temporal memory safety. This is usually used after free, that you access an object while it's already freed. This is a bit harder to do in C++. So here Rust really, with its memory model and lifetime, would help. So there you can already ensure this during compile time, that you don't have temporary memory safety issues. Overall, in this, for this study, so take it with a grain of salt. The data stuff there is not all automotive vulnerabilities. Linux kernel, for example, was not included there, but with the CVEs in this data set, it was about half-half. So half of the CVEs were due to memory safety issues. And if we also see the severity plot, some violent plots from the CVSS score, we also see that the memory safety issues tend to have a higher severity. So the buffer overflow, it's going there very to the critical reach, while, for example, the CW200 exposure of sensitive information, it's widely spread. It goes from 2 to 10. So there's a lot of different variation, while all these memory safety issues are very high, have a high severity. And to use data from a different data source, also Project Zero, they maintain some spreadsheet where they document exploits in the wild, and they also categorize them. They don't use the CWE categorization, but have their own categorization. But here you also see that exploits often use memory corruption and information leaks and use after free. So this makes 75% of the exploited vulnerabilities are due to memory safety issues. So the attackers seem to know how to exploit this kind of memory safety issues. This was the analysis of the root causes, so what we can do about it. So there was a recent paper from also Google on memory safety. So you can do three things you can try to prevent. So the easiest prevention is to not use a memory unsafe language like C and C++, like Rust, for example, or you use safe APIs. For example, if you have untrusted inputs, that you already make it through the API impossible to exercise certain undefined behavior or border bound behavior here. Then you can do mitigations. You can have a lot of compiler options, a lot of hardening techniques, which helps you to do some bounce checking at runtime. There's also going on some hardware support like memory tagging, where you can, with your computer chip, help that you don't have this, or you can detect this memory safety issues during runtime. And you can also try to put some critical stuff into a sandbox to mitigate the results of an exploit here. And also what you should do is you should detect as early as possible. So that's why we also try to do the testing and fuzzing as part of the development, because it's the easiest way to fix if we already don't let these bugs go to production. This leads us to the V model. So in the automotive industry, if we develop our software according to automotive spice, so this is some standard we use, and it's basically a V model. But of course, in the agile world, we maybe have some more iterations in the lower side of the V, but overall, we do a lot of trainings to make people, developers, aware of new tools, like how they can use Rust, how they need to write fast tests. We have like basic requirements, of course, nice compound word, group KGAS, like it's Konzern Grundanforderung Software. So also Vineeth has, I think, something on this. This is if you want to do business with VW or deliver software, you have to follow these guidelines. Then we do secure risk analysis before the implementation. So there we try to see what are the risks, what is the attacker model, and what mitigation or controls we need there to reduce the risk for a specific component. Then during the implementation phase, of course, we do a lot of a static code analysis, secret scanning. We there try to make the SBOM topic, which we also have later and then we do fuzzing, test if all the binary hardening mechanisms are in the product or not, if the debug ports are closed and so on. And then in the last step, we have the continuous fuzzing, continuous vulnerability scanning, and the whole vulnerability management. So this, let me give to Joy, who will tell us something about the supply chain.
Yeah. So now let's talk about the supply chain security and where it gonna come back to us. So typically in the manufacturing world, the idea begins at before of the production 2 to 5 years ahead. So we ask for our suppliers, get the quotations of procurement checks, and all the of all the life cycle management is managed from there. And after the vehicle is on the road, we need to maintain certain regulations from global various regulatory perspective. That means the vehicle may need to be roadworthy. It depends on the country and regulations from minimum to 10 or even 20 years down the line. That's give us to the perspective of where it gonna come back to us, that in each of the countries have their own variations of the procurement guidelines as well as roadworthiness guidelines. So each country have their own. I'm not going to go into the details, but again, this idea is evolved from the NTIA, minimum elements of software bill of materials, why we need and why it is going to the forward. As we see from automotive perspective, particularly the UNSC compliant countries are 155, 156, and part of the R157s are critically important to get the homologation type approval for a series of manufacturing start of the production, as well as US also have their own set of compliance check. So it is very important that we understand the supply chain complexity, and in manufacturing world be more proactive than reactive, because the use cases start from before 3 to 5 years of the production till next 10 years at least, or 15 years. So around 10 to 20 years ballpark area. So let's see how we drive from supply chain security challenge to the SBOM in the solution space. So as we know from the typical definition of SBOM, it is a inventory of component used to build software artifacts, artifacts such as software application or some products. And now the question is, why it become over the time, we all learn from our experience that it become critically important, particularly in supply chain security aspect. So at the before the start of the production, when we are in the development phase, we typically start from the procurement clarification or compliance like K-gas and other compliance. There we perceive the possible risk identifications. If that pass through, then when pre-development or prototypes aspect, we identify the potential software or hardware risk. And when the production begins, we come with a huge amount of security incidents, like my colleague Andreas explained, or even license claim like GPL or LGPL or specific BSD or unknown author or copyright license violation claims, as we all know about. And to understand the whole problem phase, we understood that SBOM is the way forward to find this light at the end of the tunnel. From there, we can derive not only the cybersecurity relevant information, also to improve the code or design of the architecture to extend or maintain, or the next generation architecture to evolve, like CWE, my colleague explained. And in the production of next 10 or 20 years, this live monitoring can help us to track down and mitigate, identify, detect data, and mitigate the risk like CSF or other security framework. So going forward, as we see, this is a typical Cyclone DX 1.5 example of the SBOM, having the mandatory fields and bomb format and spec versions. Others are optional, but which is important is to understand the bomb reference and how we derive the license and component information. Which is also important to understand that the PRL and the package URL and CPE help us to scale the solutions space in a automation ready and maintainable for near the future. Going forward, the next step we identified there's the VDR or Vulnerability Disclosure Report. That is a highly potential direction where we can scale the vulnerability management. That means if we go back to NIST definition, they can identify the potentially exposed or non-exposed vulnerabilities in a various templates. For example, if we go to an example, or if we take the properties of VDR, we know that it can affect or cannot affect, it can have the impact, it can be signed, authenticated and verifiable, it can be ensuring that it is compliant to the NIST databases and stuff like that. What is important that the most recent SBOM formats like SPDX 2.3 or CDX 1.4 onwards, they by default support the VDR. Now, as we have, let's go to the one example as was trying to demonstrate. So, sorry. So here we see one sample example like the CVID, the source, and the scoring, which is taken from NVD 2.I API, and we have the disclosure, the impact area here. So it affects this person from there to there, and this is the reference package signature. In the same way, we can scale this approach, but we have realized that VDR is very much generic. We can also focus on the specific goal-oriented approach that whether it affects directly or not to make it more deterministic. So there we came into the understanding that CISA is working on the vulnerability exploitability exchange format. The first definition was released a few years earlier, 22, and is being extended by the multiple working group going forward, and we would like to show how it can be more effective. So here it is deterministic main. Directly we can look at the field of the VDR's VEX part, which is also compatible with CSAF 2.0 onwards, that the state is affected or not affected or under investigations or fixed and stuff like that. And also CSAF has their own matching table 2.0 onwards, one of the profiles like affected, exploitable and stuff like that. So that way the VEX simplify the generic VDR approach to more focused on deterministic approach. We can directly ask the supplier for a specific product or component, give us a VEX, and we can automatize, or supplier can itself automatize the VEX generation and share us a disclosable report in a confidential way. That way, each supplier in the chain of the full stack, they can uniquely and confidentially share their disclosure report up to the OEM or manufacturer without leaking or risking any copyright or legal or vulnerability risk, as well as they are complying to all the regulations in place and making their process from their side as well as to our side to more effectively automizable. That means more efficiency, less manual work, like any classical work like Word, table, PDF, or text files, and all that can be obsoleted going forward when we able to use the right tools at the right problem. Going forward, I would like to hand over to my colleague for the more advanced upcoming crypto bomb. Andreas, please.
Yeah,
take over.
thanks, Joy, for the Vex. Let's go to the next slide. So the upcoming things. So now, if we would have all implemented this, like SBOM, Vex, VDR, the next thing would be crypto bills of material. So what is this? So as you know, cryptographic algorithms like can decay, can be deprecated. For example, in the past, like we have DES, MD5, SHA-1, they all are broken and you should not use them anymore in production. In the future, if there will be quantum computing, RSA also will be broken. We need something different. Key material doesn't last forever. It can be invalidated. It can be, it has an end of life date. So what we need is we also, besides normal asset management, we also need a cryptographic inventory asset management. And how do we achieve this? We could start with something like a finer grained SBOM. For example, here we see a Conan file. So this is the package manager for C++. And for some libraries, for example, libbotan, which is a crypto library, you can tell what part of the crypto library you want to use, and then only these parts will be compiled and configured into your system. So you can say, I want a UUID, I want a random number generator, and I want the SHA-256. And you specify this, and you could already express this in, for example, cyclone-dx in the data field, where you could specify the configuration and then tell, okay, this is the configured modules I have. But the downside here is that not many tools support this, and also a lot of libraries don't have this fine-grained configuration techniques. So we need a more standardized way here, and the answer here is CryptoBomb. So on the right side, you see how this would look like. You have your classical SBOM component, and then you would have like a subcomponent that you say, okay, this component offers this cryptographic asset. This is a hash algorithm and has this OID. This is for some cryptographic algorithms, they have specific IDs you can look up in some databases. And yeah, the nice thing is this was proposed by IBM. They made some proposal, and now this will be joined in the next cyclone-dx standard, which will be standardized, I think, in the end of March, beginning of April. So it should be arrived very soon. And then we can have this data in the standard way to exchange between the suppliers and us. And how we can get the CBOM is with, of course, that we need more tooling. Currently, there's not much tooling in this area. But what we did, for example, we can use like static code analysis. On the right side, you see this is the query from CodeQL at GitHub, how you would find insecure crypto algorithms like DES and so on. So they do a regex search on function calls. So internally, they have the abstract syntax tree, and then you can search where this function is called with this regular expressions. And if you know your API, you can search for specific function calls. This is most of the things, but some things are not known during static compile time. So for example, if you have a runtime configuration or you need to negotiate a cipher, you cannot be 100% sure what algorithm will be used during runtime. So there you also need maybe some dynamic analysis. So when your system runs, you need to determine what cryptographic algorithms are used. Just to sketch this up a bit. So for example, you have like one cryptographic library which offers certain certain functions. Then you can build a C-bomb and tell, okay, this function offers this and that algorithms. And then on the other side, you have your application library. You generate an S-bomb, then you search for all the calls to the crypto library, and then depending on this, what you found there, you can then reference the crypto bomb from the your crypto library. And of course, if everyone uses your one crypto library, this is much easier than everyone pulls in their own crypto library, or the worst thing, they would roll their own crypto, then it gets very hard. So giving now to Vineeth.
Yes, so thank you, Andreas and Joy. Yeah, so I will try to just give some brief overview, like on the automotive side of the vulnerability management that we are doing, and also like some of the challenges that we have, because the overall automotive system, it's a very complex one. And moving forward, okay, it works. Yeah, I mean, from the vulnerability management perspective, like we divide like the whole ecosystem like into three parts. One is the ECUs, like where the electronic control units, Andreas already introduced that, and then we have the functions, which are running on them. Something like it could be any third-party application, or the climate control, or your remote, wake up or unlock functionalities, or any such things. And then we have the third part, which are the services like the TLS, or the secure onboard communication, or the key management, which is used inside the car. And again, the whole part of the vulnerability management, I'm only speaking from the product security perspective, and we ignore what happens with the backend functionalities. And moving forward, normally, I mean, for us, some of the things like how it's placed is, we always have a bunch of suppliers and sub-suppliers that are involved, like with all of these things. Like we cannot build everything on our own. So some of the ECUs, like we source from our suppliers, and sometimes like it's just one supplier, and sometimes like we have like tier 1, tier 2, tier 3, and it goes on. And then we have the integrators. We sometimes like they are internal, like we do it ourselves, or sometimes even they are contracted. For example, if somebody develops a function which overarches a couple of ECUs, then we have an integrator between these two, between the ECUs and the functions. And similarly, we have the services, like also like have integrators, like who are trying to, or you can, call them something like, the system integrators, I would say. And for us, the other challenge is we do this for the entire VW group. So it's not just one particular car or one particular product we're talking about. It's for the entire group, like including Audi, Porsche, Bentley, Seat, VW, and all the other brands. And moving on, the other part we realized from the vulnerability management. Normally, I mean, people tend to associate this with like what happens like with the release and the response. Sometimes, like as in the vulnerabilities show up in the product, and it's more of to say a reactive way. Whenever a vulnerability is discovered, then we tend to handle it. But in our case, like we are trying to be more proactive and try to get involved in the entire V model that Andreas showed. Like we provide trainings, like, or share our knowledge on the vulnerabilities that we discovered previously, and educate the teams like on how to avoid this. And we give feedback towards the requirements itself, like to make the requirements much more stronger and better. And also we get involved during the design stage as well, and provide our feedback. And so we are pretty much involved, or try to get involved either in an active way or in a passive way in the entire V model, so that we this also goes like along with the shift left approach that we have, like where we are more proactive. And out of this, like we chose like five complex or like five challenges that we are facing. I mean, to say there are really plenty of it, but kind of like summarizing it into five things. Like there's always like the challenge we have of the very complex supplier matrix, as I stated earlier, with the tier 1, tier 2, and tier n suppliers. It's always, the list goes on. And also tracing the vulnerability to the source, it's always a challenge. I'll explain it more later. And also prioritizing the vulnerability reports that we receive. We have multiple sources like from which we receive vulnerabilities, like from scanning and from bug bounty programs, and from also like the penetration tests and our own internal offensive security teams. Yeah, and also there are really nice talks on prioritizing the vulnerabilities in this conference already earlier. And also, and the other challenge is ensuring that every patch is thoroughly tested and delivered on time. And this is especially most crucial for us because sometimes like the car is already out on the street with the customer, and then we need to make sure that nothing breaks, and because sometimes it can have serious implications, like somebody is driving on the autobahn over here like at 200 or 300 kilometer per hour, and then there is a vulnerability somebody can exploit remotely. It's not a good case. Or we have fixed the vulnerability but it's not tested properly. So yeah, we have to really consider these factors as well whenever we deliver any patches, because so many lives depend on it. And just as an overview, like the out of some recent studies, like the average life of car is around 10 years. And and in Germany especially, like it's around 14.8 years, like until people scrap their car. So we have to provide the support until this time, or at least ensure that there are no major vulnerabilities which are affecting soon. And going on a bit about what does the regulation states. I mean, I only focus on a couple of regulations from the perspective of the Europe. It is the United Nations Economic Commission for Europe, like they have, or in short, like UNECE, they have certain regulation requirements towards the vulnerability management. And in terms of the process itself, they state like we should have a process in place as part of our CSMS system, or the cybersecurity management system, that we monitor, detect, and respond to any kind of cyber attacks, threats, or vulnerabilities on the vehicles. And and it says like we should have, and the interesting part is like it says it should be mitigated within a reasonable time frame. So this is for the UNECE. And for the other thing, I mean, I just go to the China GPT because this is like where I'm also like working on right now. There are of course like many other regulations from other countries as well. And the China GB regulation, like it is still in draft, the whole vehicle cybersecurity regulation. It will come into place sometime like from 2027, 28. Like this is still like our forecast. And and over here it states like the vulnerabilities with a high risk or above must be handled within 6 months of time. So this is like what the couple of regulation states. But and also now going into the like how normally like our product life cycle look like. We start the car project and we have many minor software releases like from all our suppliers, and then we set major maturity milestones which we achieve, like where we integrate all the things like and test the whole system is tested thoroughly. And after reaching like the maturity milestones we have set, then we start the production, and then it goes on like with the over-the-air updates until the end of the life cycle of the car. And again, coming back to the holy trinity like of the ECUs, function and services, like we face some really hard challenges, as in what happens like if the suppliers or the sub-suppliers or someone else like goes out of business, like after SOP, as we saw, like the average life cycle of the car, like if we assume it's around 10 years, then we need to provide software support until then for any kind of vulnerability that comes up. And because the automotive side is heavily dependent on the suppliers, we cannot have everything on our own. It's very crucial that we have some kind of a system in place if they go out of business. And also, we should also consider the financial model, like if a supplier has delivered something and if there is a vulnerability over there and which we want it fixed, then the suppliers will normally not do it for free. We should also have a robust financial model in place to tackle this. And in the end, somehow this will reflect back on the customers. So we try to come up with a much optimized financial model as much as possible. Okay, looking at the time, have around 6 minutes, so I'll hurry up a bit. So to tackle this, like from the VW group, like one of the obvious solution was like we try to shift from a supplier-based model into own in-house development. And this is also the reason like why CARIAD was formed. And we analyze like what makes more sense like to develop in-house and what makes sense like to get it done by the supplier thoroughly, and then we try to build it in-house. So because we cannot completely remove the suppliers, we also have some very strong requirement towards the suppliers, and one of it is the VW KGAS or the KAGAS, and in German it's Concern Grundanforderungen software, where we state our basic the requirements towards all the suppliers, and they have to fulfill this in order to do business with the VW group. And moving on. The second challenge, like tracing the vulnerability to the source. Assuming, I mean, vulnerabilities can occur anywhere, either in hardware, in services, functions. Like assume like if there is the next Heartbleed version 2 that occurs, then we tend to derive the facts, as in like now we know that the TLS service is affected out of this, and we find out all the ECUs in the car which have been affected, which are using the affected OpenSSL version in it, and then we list the functions or the applications which are running the TLS services, and we should get it fixed. But again, still there are more things, as in we should see like where is the source of this package. Sometimes in the car, like we also have a lot of third-party applications like which are running who package their own OpenSSL libraries. Then the biggest challenge for us is to identify who is the owner of this risk, if it's the ECU or the function or the service. So, and quickly moving forward, so with this, we try to set up multi-directional dependency tracking among the three. And also already spoken, we have the software bill of materials. We try to do this in the Cyclone DX 1.4 or higher, as also like stated by the BSI requirements. So it's not automotive relevant, but we still follow it to be at par with the industry. And also along with the software bill of materials, it's not written here, we also have a hardware bill of materials to track all the hardware artifacts that we have. And as per the UNECE R155, we have very specific security roles that are defined for the ECUs, functions, and services. We have security owners like who take up the ownership, like whenever a particular risk arises out of a vulnerability. And then the prioritizing, I don't go too deep into this. It was already spoken, I guess, in the previous talks as well. And looking at the time, we have a customized prioritization function that we follow, which includes like CVSS, EPSS, the VEX, and and everything. And this model is also continuously evolving, and out of this we derive a prioritized list of vulnerabilities, and we try to remediate them because even we cannot fix all vulnerabilities at once, so we should prioritize them. And also maybe the other thing is now there is also a cybersecurity assurance level that is being drafted and standardized as per the ISO 21434. Yes, and the last, the testing and delivering, we know like typically for in contrast to the mobile phones, we are using Android and iOS provides around 8 years, 3 to 8 years of support, and the Linux LTS kernel support is approximately 2 years. But for us, like, we have to provide much more longer support, and that means we have to maintain all the tools and all the testing and the vehicles. Like if it's a mobile phone, then like within a single roof, like you can have hundreds of mobile phones like running different kinds of hardwares and different software versions on them, and it's easier. But for us, it's cars we are talking about, so we should have every variant of the car and every variant of the software need, like, and we need to test all of them before we provide any kind of release. And also as per the solution, we try to get as much of knowledge transfer as much as possible from the supplier side, and we invest highly in the test management, and we do penetration tests all the time before delivering anything to the customers. And we tend to use as much as open source tools as possible, because anytime if we don't feel confident about any particular test we have done, we need to reproduce them all the time, or anytime, sorry. And just to summarize on the lessons learned,
Message to the speakers. We have another group coming in this room and this channel, so we are going to have to go ahead and end the talk at this time. For folks attending, please do know these materials will be available on YouTube and the first.org site. If there's anything you missed, I do want to thank Andreas, Joyabrata, and Vineeth for the excellent content here today. Let's hear it for our speakers.